Chapter 9, Circles. Today we're going to cover 9-2, Tangents. Your class opener. Point O is the center of the circle. Name each figure. And our objectives for today. After studying this section, you'll be able to apply the theorems that relate tangents and radii and recognize circumscribed polygons and inscribed circles. Theorem 9.1. If a line is tangent to a circle, then the line is perpendicular to the radius drawn to the point of tangency. So the big fact here is if you have a tangent and you draw in the radii, the big thing is they end up being perpendicular and give you a 90-degree angle. Corollary. Tangents to a circle from a point are congruent. So if I look at the figure right, here's two tangents that both go through the same point. So the tangent piece on this side is going to be congruent to the tangent piece on the other side. So from that point to where the tangent intersects the circle on each side is congruent. Theorem 9.2. If a line in the plane of a circle is perpendicular to the radius at its outer endpoint, then the line is tangent to the circle. So it's sort of like what the first one was saying, except for in reverse. It's saying, if I give you a circle, and I tell you that I have a radius in the circle, and I tell you that at the end point of the radius, there is a line that happens to be perpendicular. So I have my radius, I have a line that goes through the endpoint, and it's perpendicular, then I know that this line on the outside could be called a tangent. Number 1, if OT equals 6 and JO equals 10, then JT equals what if it is a tangent to the circle? So if JT is a tangent to the circle, I know that this is going to be a right angle. They told me that OT was 6, JO, the entire length out here, was 10, and they want me to find JT. So this is just the Pythagorean theorem where I'm missing either my A or B value. I'll call it B. And now let's see. So I have 6 squared plus B squared equals 10 squared. 36 plus B squared equals 100. Subtract off 36. B squared equals 64. Square root each side. And I get 8. So JT is going to equal 8. Given segment TR and segment TS are tangents to circle O from T, the measure of angle RTS equals 6. Part A says copy the diagram, draw segments RS, and find the measure of angle TSR and the measure of angle TRS. So let's start filling in the information we have. I know that segment TR and TS are tangents to the circle. Since they come from the same point, I'm just going to mark in that I know that they're going to be congruent to each other. I know that the measure of RTS is 36 degrees. So up here I have a 36-degree angle. In part A, it wants me to draw in segment RS. So drawing in RS. And it wants me to find the measure of angle TSR and angle TRS. Well, it wants me to find these angles, and there's something sort of important that I know. I know it's an isosceles triangle because the tangents are congruent, so I know that these two angles are really the same size. So the easiest thing for me to do is to just grab my calculator. I know that all the angles in a triangle add up to 180 degrees. So if I take 180, subtract off the 36 degrees I have at the top, I'm left with 144, divided by 2 between the two congruent angles, and I know that each of them is going to be 72. So up here, I can even write in that they're both 72 degrees. Part B, draw radii OS and OR. So I'm going to start with that. I'll just freehand these in. So here's OR, here's OS. And find the measure of angle ORS and OSR. Again, I know that since these are radii, they're going to be congruent. So these angles that I'm trying to find out here are going to be congruent to one another. Well, how can I figure out how big those angles are? Well, the sort of nice thing is, I know that out here tangents form 90-degree angles. So if I can just take 90 and subtract off 72, I can find that those angles, 90 minus 72, are going to be 18 degrees. And then finally part C says find the measure of angle ROS. Well, if I'm looking at the small triangle, and I think again, I know that all the angles in a triangle have to add up to 180. So if I subtract away the two 18-degree angles that I already have, I'm going to be left with 144. Segment SR is tangent to circle P and circle Q. QT equals 5, TR equals 12, PR equals 39, and I'm supposed to find PQ, PS, and ST. Well, let's start filling in the information that I do know. If SR is tangent to circle P, I know that it's going to form a 90-degree angle here, and if it's tangent to circle Q, I know that it's going to give me another 90-degree angle there. Filling in the values, I know that QT is 5. I know that TR is 12. And I know that PR is 39. And they want me to find PQ, PS, and ST. So finding most of the other pieces in here. Well, let's see how we can find that. If I look right now, I notice that I see two similar triangles. And the reason I know that they're similar is the small triangle over here has a 90-degree angle. The large triangle also has a 90-degree angle. And both triangles share angle R out here. So by angle, the triangles are going to be similar. So I should be able to set up a proportion between them to find the missing sides. Now, before I do that, I'm going to actually go through and find how big is QR in my little triangle. And if I look, I see that I could call that C and do the Pythagorean theorem. So 5 squared plus 12 squared equals C squared. I get 25 plus 144 equals C squared. Add that together, 169 equals C squared. Square root each side. And I get that that piece is 13. So now if I think of setting up a proportion for similar triangles. Well, setting up a proportion, if I do all three sides at the same time, I know my little triangle has side pieces 5, 12, and 13. In the large triangle, the piece that corresponds to 5 is going to be PS, which is one of the pieces I'm trying to find. The side that corresponds to 12 is going to be SR, which is not one of the pieces that I'm trying to find. And then the side that corresponds to 13 happens to be PR, which is not one of the pieces that I'm trying to find either. I'm trying to find PQ, and notice I can find PQ really quickly right now. If I notice that PR is 39, QR is 13, if I just take 39 and subtract off 13, I'm going to get that this piece is 26. So PQ right away I know is 26. ST, I don't know how big ST is, but if I figure out SR, then I can figure out how big ST is. So figuring out SR is going to be important. So looking at my proportion, I need to know one of the values on the bottom to be able to solve this. And I notice that I actually know how big PR is. PR is 39. So I'm going to come up here and change this to 39. I notice I can reduce by 13. And now I'm going to cross multiply to figure out how big the value of PS is first. So if I cross multiply 5 over PS with my 1/3, I get PS times 1 is PS, 5 times 3 is 15, and I've just found out that PS is 15. Now if I go ahead and cross multiply 12 over SR with 1/3, I get SR times 1 is SR, 12 times 3 is 36. So I know the entire side up here, SR, is 36. If I subtract off the 12, I get that ST is 24. A polygon is circumscribed about a circle, and the circle is inscribed in the polygon if each side of the polygon is tangent to the circle. So notice on the left here, the circle is inside of the triangle, and each side of the triangle is a tangent to the circle. Or on the right, the circle is inscribed in a quadrilateral because every side of the quadrilateral is a tangent to the circle. Common tangents. If I look, I have two circles on the right, and I drew in a dashed line that connects the centers together to help me describe different types of tangents. The first type of tangent is an internal tangent. The tangent intersects the segment connecting the centers of the circles. So if I imagine coming in here and drawing in an internal tangent, here's what it would look like. It's going to be a tangent that touches one circle and then also touches the other circle, and it just so happens that this line passes through the dashed green line that connects the centers together. So there is an internal tangent. It's tangent to each circle, and it passes through that line that connects the centers of the circles together. I then have something called an external tangent, and the tangent does not intersect the segment between the centers of the circles. So if I imagine now drawing in a tangent, and this time I'm going to draw in a line that's tangent to both circles. So it's going to intersect each circle in one place, but notice that the line doesn't pass through that line that connects the centers of the circles together. So the blue line is an internal tangent, the red one is an external tangent, and it all depends on would it pass through the line that connects the centers of the circles together. Tangent circles. Coplanar circles which intersect at just one point. So here are some internally tangent circles. The circles are all tangent, meaning they intersect in one place, and one circle is inside of the other circle. Externally tangent circles are tangents where one circle is not inside of the other circle, and they still intersect in just one place. And here you can see a bunch of different pipes all stacked up. You can see a bunch of them having external tangents, and hopefully you can find the couple that are internally tangent. And your closure. The main idea of today's lesson was